Every steel wire, every suspension bridge, and every reinforced tire begins here.
This is hematite. Its chemical formula is Fe2O3. To be economically viable for steelmaking,
Before we can scoop, we must shatter. The rock is too dense for even the largest excavators. We begin with the drill.
Tungsten carbide teeth grind through the crust, creating a grid of holes 15 meters deep. These are not random, they are
Detonation. In milliseconds, thousands of tons of solid rock are converted into a manageable pile of rubble.
Enter the electric rope shovel. This machine runs on 72,200 volts of electricity. Its bucket alone can hold one.
It loads a haul truck. These Titans carry 400 tons of payload. The suspension cylinders are pressurized with nitrogen.
the tires alone cost $40,000 each. They must withstand immense heat and friction as the truck climbs the 10% gradient ramp out of the pit.
The ore is out of the earth, but it is too large for the furnace. It must be crushed. The journey from rock to wire has only just begun.
The primary crusher works like a mortar and pestle on a gigaton scale. An eccentric shaft gyrates the steel mantle.
We must separate the treasure from the trash. Using magnetic separators, we exploit the natural magnetism of magnet.
To fix this, we bake a cake called sinter. We mix the iron dust with coke breeze for fuel and limestone.
The mixture is fed onto the center strand, a continuous moving grate. The bed is 500 mil.
It passes under the ignition hood. Gas burners set the surface on fire at 1200 degrees Celsius, but the heat doesn't stay on top.
Of course. Massive fans below the belt create a vacuum, sucking air downwards. This pulls the burn zone through the entire depth.
The result is a porous, clinker-like rock. These holes are crucial. They serve as airways, allowing hot gas.
At the end of the strand, the solid cake is crashed and broken into uniform chunks. It is now stable, porous, and rich in iron.
Cooled and hardened, the sinter is ready. It rides the conveyor to the heart of the factory. This is the heart of the steel mill. The blast furnace, a vertical reactor that runs continuously. The furnace is hungry. Every minute, the skip hoist delivers tons of sinter and metallurgical coke to the
Uniformity is critical. A rotating chute distributes the layers precisely. If the pile is uneven, the gas will.
To melt rock, fire isn't enough. We need a blast. These stoves preheat air to.
Through copper nozzles called tuyères, the hot air meets the coke. The carbon ignites instantly, raising the temperature.
The burning coke creates carbon monoxide gas. This gas strips the oxygen atoms away from the.
The liquid iron pools at the bottom. To get it out, we don't open a door, we drill a hole. A pneumatic drill pierces the refractory clay plug. Release. Molten pig iron, at 1500 degrees Celsius, rushes out. It flows like water but carries the density of metal.
Physics separates the product. Iron is heavy and sinks. Slag, the melted limestone and impurities, floats on top. The skimmer. The iron is caught in a torpedo car, a giant thermos on wheels lined with refractory bricks. The iron has arrived. It contains impure, which makes steel weak.
Steel is 100% recyclable. We start by dumping 50 tons of solid scrap steel into the vessel.
Then, 200 tons of liquid iron are poured on top. This is the most dangerous moment in the mill. Any moisture in the scrap, the vessel stands upright. Enter the oxygen lance. This water-cooled copper pipe will lower to within 2 meters of the liquid bath.
Ignition. Pure oxygen is blown at supersonic speeds, Mach 2. It hits the molten iron with such force it creates a cavity in the liquid.
The pig iron has 4% carbon. We need it below 0.1%. As the oxygen burns the carbon, it triggers an exothermic. Lime is added to create a liquid sponge called slag. It absorbs silicon, phosphorus, and manganese. After 20 minutes, the blow stops. We tilt the vessel for a turndown. A sensor measures the temperature and oxygen level.
We tap the steel through a small hole to keep the dirty slag behind. This is no longer iron, it is liquid.
For wire rods, we need precise flexibility. We add ferromanganese and silicon. The steel is stirred with argon gas.
We cannot simply pour the steel into molds like a cake. We need a continuous, endless shape.
If liquid steel touches air, it oxidizes instantly, ruining the quality. We protect the stream with a...
The steel enters the tundish. This vessel acts as a buffer tank. It calms the turbulence of the pour and
This is the critical moment. The steel enters a water-cooled copper mold. Copper is used because it conducts heat away faster than any other industrial metal. If the mold stayed still, the steel would stick to the sides and tear. The mold oscillates, jump down.
Leaving the mold, the steel is a billet, but it is fragile. Only the outer shell is solid. The center is still molten liquid.
Gravity takes over. The strand is guided through a curved arc. High-pressure water sprays freeze the core, forcing the crystal.
At the bottom, the withdrawal straightener grabs the strand. With immense hydraulic pressure, it unbends the steel from a curve. The process is continuous, but we need specific lengths. A flying torch clamps onto the moving steel, cutting.
These are 150 millimeter square billets. They are the raw currency of the rolling mill.
The billets are solid, cold, and unyielding. You cannot roll cold steel without shattering them. They enter the reheating furnace. This is not just an oven. It is a precision thermal machine capable of processing 100.
Inside, we use a walking beam mechanism. Unlike a pusher furnace that scrapes the steel, this mechanism lifts the billet.
The journey takes 90 minutes. We don't just heat the surface. We must soak the heat deep into the core. If the center... Precision is key. Too much oxygen in the burner mix, and the steel will literally burn away, turning into useless scale.
Target temperature reached. The discharge door opens. The billet is now a glowing battery of thermal energy, soft enough to be molded like clay.
But there is a problem. The heat has reacted with air to form scale, a hard crust of iron oxide.
The solution is high-pressure water descaling. We blast the surface with 3,000 psi water jets. The thermal clean, hot, and homogeneous. The billet is ready for the most violent part of the process, the high-speed rolling mill. The rolling mill is a series of 25 to 30 stands. The first impact happens at the roughing mill. Here, we cannot squeeze it from one side only, or it would pancake. We use an alternating horizontal-vertical sequence. The front of the bar, the nose, can be deformed and cold. A computer-controlled crop shear calculates the speed.
Physics dictates the rules here. The law of conservation of mass. Since the volume of steel remains constant.
If one motor pulls too fast, the wire snaps. If too slow, it tangles. We use loopers.
Friction generates immense heat. To stop the grain structure from growing too large, we blast the wire with water between the stands. We reach the no-twist block. Here, the rolls are made of tungsten carbide, the only material to withstand under... The billet entered at a walking pace. The wire rod exits at 100 meters per second, that is 360 kilometers per hour. At these speeds, the wire is a dangerous projectile. The pinch roll maintains the final tension, guiding the supersonic thread into the laying head.
The laying head catches the straight wire and spins it into a helix. The straight line becomes a coil. But the process is...
The rolling is done, but the steel is not finished. It enters the controlled cooling conveyor. This is not just... Beneath the rollers lie the plenum chambers, massive lungs that breathe air onto the wire. By adjusting...
For high-carbon steel, used in suspension springs and tire cords, we blast it with maximum air.
For low-carbon steel, used in screws and nails, we need softness.
We close the insulated hoods to trap.
Operators monitor the thermal profile. A deviation of just 50 degrees can mean the difference between a bridge cable that holds and one that snaps.
The overlapping pattern is not accidental. It ensures that every inch of the wire is exposed to the air evenly.
At the end of the deck, the rings fall into the reform tub. Gravity stacks them around a central mandrel, converting the continuous stream into a manageable industrial coil.
Before the coil is tied, a sample is taken. The lab must confirm that the microscopic crystal structure matches the customer's request.
The wire rod is now a continuous metal rope, miles long, coiled loosely. In its current state, the coil is too loose. It contains too much air.
Enter the hydraulic compactor. This machine applies 30 tons of vertical force. It turns a loose. The hydraulics engage. The press squeezes the air out, forcing the rings into a solid, compact block. This density. While under pressure, the automatic binding machine strikes. 4 robotic arms wrap high-tensile steel straps around the bundle.
The pressure is released. The straps hold the tension. What was once a loose spiral is now a secure.
Every coil is a unique individual. It is weighed to the kilogram. A weatherproof tag is attached.
Traceability is non-negotiable. If a tire blows out on a highway in Germany, we must be able to trace the steel back to the exact minute it was melted in this furnace.
The warehouse stores the output of a ceaseless process. Thousands of tons of inventory, waiting.
Finally, they are loaded. By train or truck, these coils will travel to downstream factories to be drawn.
While the coils cool in the warehouse, the sample travels at 10 meters per second to the central laboratory. Here,
To read the steel's DNA, we must look beneath the skin. The sample is ground and polished to a mirror finish, removing any surface oxidation that could corrupt the data.
Spectrometer blasts the sample with high voltage electrolyzing a tiny amount of metal.
Chemistry is half the story. Performance is the rest. We load the wire into the tensile tester. This machine will pull the steel until it physically rips apart.
Watch the necking. The steel passes its yield point. It is no longer elastic. It is flowing like plastic.
The failure.
The rod snaps at 1200 megapascals. This confirms the ultimate tensile strength.
Under the microscope, we verify the cooling process. We are looking for perlite, layers of iron and carbide.
We also crush it. The upset test simulates the violence of making a bolt head. If the edges crack during crushing, the steel...
Only now is the steel born. The mill test certificate is its passport. It certifies that this coil meets the
It started as red dust in the ground. Through fire, force, and physics, it has been